So, Professor Körner from Cambridge University is going to talk about new ways of looking at error.
I was going to start by saying that to some of you, it will be interesting to know that I am indeed the son of Stefan Körner, that his father said to him when he was thinking about what to do, you should neither become a philosopher nor a mathematician because you'll starve, so you should become a lawyer. And my father became a philosopher and I became a mathematician. Okay. Okay, well, there is a great variety in these talks. Mine will tend, as you might expect from a mathematician, to the mathematical side, but I hope you'll see the kind of general ideas that underlie it. Indeed, it's all summed up in this first slide. I measure a piece of wood, I get a certain length, splendid. I get a different length, tragedy. Right? What is the solution? Well, if you were, the natural thing is to tell your apprentice, measure it again, but better. So you shout at him until it's right. Well, that worked until the rise of experimental science. And then Galileo did repeated experiments and got different answers each time. Repeated experiments give different answers. So, and we're already doing our best. It's not the assistant who's mucking it up, it's us. So what do? One answer, which is the answer given by Galileo and by Newton, is take the average. So you have a lot of measurements of the length of your table. You take the number of times you've taken the measurements, you add the measurements together, you divide by the number of times you've measured. But it's not clear that this is the best. Perhaps you should take a median so that half your results are above the median, half of your results are below the median. Or, it seems rather rational, if you get something which is far from what you expect, you should throw it away. It's obviously worthless. So you first look through your experimental results, you throw away those that you think are wrong, and then you take the average of the rest. Well, that's the question. The problem gets much worse if we're trying to recover two linked unknown quantities. So we have as just an equation, ax plus by equals z. X and y are constantly changing. So after one measurement, we measure, we get ax1 plus by1 equals z1. And you know that we have too few equations to find what A and B are. Okay, so we take two measurements. And after two measurements, we have two equations, and that is exactly the right number of equations to give us the answer. So we do it 3 times. And the problem is that in general, 3 such equations will be inconsistent. So we have 3 inconsistent equations, and the more measurements we take, the worse it becomes. Which is vaguely paradoxical, and in any case, we ought to be able to do things, right? At least We either wring our hands or we do something. Okay, now let's go to historic times. In 1801, an astronomer spotted something which could be a new planet. However, after because it was between two, just the right distance away, apparently. After a few weeks, the possible planet vanished into the glare of the sun. So astronomers were left with 19 observations over 42 days. So that's 1% of the orbit. Fitting an orbit, well, we know that planets go round the sun in ellipses. We know that that this ellipse is in a plane, so, we have 6 quantities to measure, and we have 19 observations. Completely impossible, because those 19 observations aren't themselves necessarily very accurate. Then Gauss, so everybody bows their heads. The prince of mathematicians, by universal acclaim, one of the 3 greatest mathematicians of all time, took up the problem of finding the orbit. And by dint of incredibly hard work, about 100 hours of calculation, right? Not your calculation or my calculation, but proper hard work calculations. And the new techniques produced a solution. And when astronomers looked, there it was. Absolutely marvelous. Now, there's a hell of a lot going on in Gauss, in this single set of calculations from Gauss. But Gauss placed great weight on the fact of how he had dealt with too many inconsistent measurements. And he said, I have used my method of least squares, which of course led to a priority dispute because Legendre another mathematician, Legendre, had independently produced this idea and published it, and Gauss had not bothered to publish it. But there seems little doubt that both of those were independent discoverers. So it's this method that we're going to discuss. Simplest example is when we have 3 equations, but only 2 unknowns, A and B. Whatever A and B we choose, we won't get, we can't possibly get Z1 and Z2 and Z3. We get plus an error. So we choose X1 and Y1, we choose A and B, X1 and Y1 are given to us, X2 and Y2 are given to us, X3 and Y3 are given to us. They produce not the true value, which is Z, but the Z1 and Z2 errors. And Gauss says, minimize the sum of the squares of the errors. So we choose E1 and E2, and we choose X1, X2, Y1, Y2 as much as possible to get the. And you say, is that all? Well, we try the problem and we minimize, we find A and B which minimize them, and we find that we get 2 linear equations in 2 unknowns, and this we know how to solve. So what we have, whether it's a good method or a bad method or a completely lunatic method, is at least a feasible method, right? It gives us a rule for finding if we have too many observations, it gives us a rule for finding what the underlying constants are. Okay. Now, this is not an isolated thing. Gauss, everybody realized that the least square method will work in exactly the same way in a large range of cases. That is to say, it delivers the right number of simultaneous linear equations. And such systems can be solved in a routine manner. Now, routine, of course, it depends on the fact that algebra has advanced in the 400 years before Gauss. It also depends on the fact that Gauss was an expert calculator. Those of you who have done a little mathematics will know about Gaussian elimination for linear systems. You can solve them by Gaussian elimination. You may also know, well, other techniques which Gauss invented. But how do we justify it? Well, in the case of this small planet, this planetoid, if he'd got it by sacrificing a goat, astronomers today would still be sacrificing goats, right? It works. What more do you want? This apparently impossible problem has been solved. And that's all you need to say. But what about the usual situation where there is no independent means of solving the result? Well, Gauss, prince of mathematicians, spent 13 years mapping the kingdom of Hanover, right? One of the great mathematicians of all time, spent 13 years getting up early in the morning, going through wind and rain, talking to surveyors, inventing instruments and so on. How do you do it? Well, as already was done, you take some high spots in the country, church steeples or mountains or whatever, and from there you observe other church steeples or mountains, and that enables you to get a series of triangles governing the area to be mapped. Does that a few nods, right? Now, if you walk to the top of a high hill in England, you will find a little concrete thing, which is where they put the instruments. So you took your instruments, you looked at the distant hills, you got these triangles. Now, there will be errors. All sorts of reasons for errors, right? And that will show itself in that, for example, even if we were to take one triangle, so we have three church steeples, and we make observations from each church steeple of all the other church steeples, then the angles will not add up to 180 degrees because I'm sorry, I did miss out one important point. You also have to have a baseline somewhere between two of your church steeples so that you actually have one length that you know, and then you can fit all the triangles in like that. Now, if you apply Gauss's method, minimizing the squares to these arguments, what you discover is that Gauss's recipe says, take the difference between 180 degrees and the angles that you've measured, divide it by 3, and put it equally among the other angles so that you now have a triangle which adds up to 180. If you are triangulating a country, then you can't quite do that because you've got a network of triangles, and from many hills or steeples, you will be taking measurements of 3 hills, and then the angles have to add up to 360 degrees, right? So you have this further constraint. So you have a lot of constraints, but once again, the magic works. The least squares estimate gives you exactly the right number of equations in exactly the right number of unknowns, and they are linear equations, and they are relatively easy to solve. And so here we have a second justification. Here, you don't know, you can't verify your triangulation. You can do it again, but you perhaps in 100 years, somebody will retriangulate. Expensive business, but you could do it and get the measurements even more accurate. But for the next 100 years, we're stuck with it. So why do we use it? Well, ease of calculation. Now, ease of calculation is relative, but so far as everybody is concerned, it's easy to do. It gives reasonable answers, right? I've shown you in the case of a triangle that it gives a reasonable answer. In general, it gives a reasonable answer. And it is the generally used method. And that really is sufficient. We don't need to worry about deep philosophical things. It is a good enough method. Now, Gauss, of course, sought, oh, and let me say that, yes, it sounds a terrible waste that Gauss should spend 13 years surveying the Kingdom of Hanover, but remember, he then went on to found differential geometry, the geometry of surfaces and so on, so well worth time. So Gauss sought another justification. So he looks at the estimation of a single quantity by many measurements. So this is again returning to measuring a table many, many times. Right. Well, there's only going to be a single length, and we're going to have the measurements. So we are going to minimize the method of least squares calls on us to minimize the sum of the squares of the difference between our estimate and the actual measurements. And what Gauss said is very interesting, and he said, look, chaps, most people say that if you have a lot of measurements, you should take an average. That's what most people say. Not everybody, but most people. If we estimate a single quantity by many measurements, then under certain assumptions, the only probability distribution for which taking the average is always correct. Right? Correct. Whatever you start with, you should have taken the average, is if you get what is now called the Gaussian or normal distribution. The last lecturer mentioned the Gaussian distribution. I shall tend to call it the normal distribution, but it is the Gaussian distribution. And you had a picture. Okay, the picture that he says, what are we going to assume? The graph of the distribution is symmetric. You're as likely to make a positive error as to make a negative error, and it's okay. You may say, well, that's not always going to happen, but very often it's going to happen. The graph of the distribution has a unique maximum. Well, we call such things bell-shaped. Anything that looks vaguely like this is, and we want to maximize the probability that the mean is close to the maximum of the distribution, then only the Gaussian distribution will work. And that is a fairly strong thing. It is, of course, true that people now refer to the normal distribution as the bell-shaped distribution. But this is really ridiculous. Almost every distribution you can think of is bell-shaped. The particular bell shape is Gaussian. And then he also shows, so this is another justification, that if the errors form the normal distribution, then under a very wide range of circumstances, the method of least squares is the best one to use, right? And if you were taught a first course in statistics, that was what you were taught, or perhaps a second course, right? I mean, if you become an actuary, you're told all distributions are normal. So Gauss says, and his argument is completely watertight, as you would expect from Gauss, that if we're happy with averaging to deal with estimations, then we should be happy to assume the law of errors given by the normal distribution, and so with method. And of course, normal distribution, you've already seen it, it was in the last lecture. These curves are the normal distribution. But why should nature be so kind as to meet our expectations? The Poincaré, not as great as Gauss, but pretty good, quipped, everyone believes in the law of errors. The experimenters, because they suppose it a theorem of mathematics, and the mathematicians, because they think it is an experimental fact. That wasn't even fair then. If you were part of the Russian mathematical school, you knew better. But that was the general opinion. Right. And the first very important step was taken by Laplace, who linked his result very clearly with the method of least squares. He showed, well, first he showed he revisited an old result of de Moivre and partly reinterpreted it, but mainly improved it to show that if you threw an unfair dice many times, the result would always resemble a Gaussian error curve. Right? He proved that. And then he went on to effectively show that this was true. If you have a lot of independent small errors, they will add up to something that looks like the normal distribution. And his proof was a bit vague even for those times, but it was basically right. The problem was that he didn't put conditions when you would expect it to be true. And particularly through the first few years of the 20th century, this law was actually proved. Well, as I say, Laplace proved it, but we've now tightened our grip on it. If there are many small independent sources of error, we may expect the result to roughly follow a Gaussian distribution. So if you work for the National Physics Laboratory, if you work in metrology, if you work in anything, you don't say this, because there are a lot of errors, this is going to be normally distributed. Because firstly you have, because it might not be. You might have underlying causes of which you don't know nothing. But it is your first stop, your first try is to say it is quite reasonable to suppose that the error is Gaussian. Let us see what we can do with it. If it turns out that we're wrong, well, it will appear. But so I think that that is where I stop. Thank you.
Thank you. Well, we've got time for questions.
Yep.
I just wonder if this. I was thinking is Gauss talk anything about central limit theorem in his time?
I don't believe so. I believe, as I say, he gave several justifications, but he must have. I mean, I do not think there is any evidence, but I may be mistaken.
Okay.
I mean, although Laplace and Gauss really did consider the rest of the world not quite up to their standard, they did read each other.
Yeah. Another thing, most of the cases we come across non-normal distribution of data. You know, even though we are getting a lot of data and it looks like it's not normally distributed, then what is your suggestion about the error calculation about such data set?
Well, again, there is this thing I talked about with land measurement, right? That it provides a conventional thing to do. So when somebody says, we have proved this atomic particle exists with probability outside 4 sigma, then you don't mean that nobody believes that the probability it exists is actually that small, right? But you have to stop somewhere. There is some point at which you have to say, at least provisionally, we will accept this particle. And it works. So it provides a starting point. And also, even in cases where it's not an exact normal distribution, it may be close enough to enable us to do simple calculations.
There's a question at the back.
I really enjoyed that. Thank you. Talking about Ceres, the dwarf planet, the astronomers then, making their measurements over that brief 1% of the orbit, did they discuss error introduced by the speed of light?
Well, the answer is I don't know, but let me think. When speed of light is, I mean, somebody with a history of science, I tend to think of the speed of light first being measured later on.
Thank you.
There's down at the front here in blue jacket.
I don't quite know if there's a question there, but even if you assume, it's kind of probably worth noticing, even if you assume that the distribution is another one and you attempt to do something like maximum likelihood estimation, you will still use that trick of the sum of squares as what you try to minimize, at least initially.
At least initially, but
Yeah.
you're not. You do it with less confidence. You really
Yes.
are going to do it with. Okay.
Yeah, but the thing is, the sum of squares trick unknown to Gauss became even more important in other contexts as well, right? Because it was easily differentiated, easily computed. And today, even with computers, we're not necessarily bound to that. We could just as well, kind of minimize standard deviations rather than variances and so forth. But that trick still is sort of dominant in all approaches to measurement and error.
Okay. I think the answer to that is it's very difficult to do other estimates without a computer. With a computer, you can do things like minimizing not the sum of squares, but the sum of absolute values. Now, under certain circumstances, that may be a better way to approximate things, but you would need a lot of evidence to use it in statistics, right? That's why, right? All these arguments of Gauss and Laplace and so on, none of them is absolutely watertight, but you have to have but they together give a very good case for using sum of squares. But as I say, for certain circumstances, if you're measuring X-rays on things, you might well wish to use a different standard of error, but for reasons that are understood, right? And there the errors are not, it's not so much statistical thing as curve fit. Yes, I'm sorry, for curve fitting, where you just want to fit a curve, it may make more sense to use absolute value, though there's an awful lot to be said for using squared values. And for some circumstances, you do that, but it's not really a statistical thing.
There's a question just in front.
You've talked about the mapping of Hanover, and obviously, of course, many other countries have been mapped out by triangulation in the same way. Obviously, Britain and India, and I don't know where else. And then, presumably, they got checked when new triangulations were made later on. And then later on again, we've got satellite mapping, which presumably can check these. So I'm wondering, did he get it right?
Okay, the answer is I don't know, but these things, as I say, it's unlikely to have been important enough, right? What do you need to measure to within a meter, right? We can now measure to within a meter, but they couldn't then, but sorry.
Yes, as you brought in my profession, I'm amazed that Gauss spent 15 years with such a fairly, it's not trivial, I make my living out, I'm not a cartographer, I'm a building surveyor by trade. I can measure things, and that's the most important thing I do, whatever it is. I normally say approximate because that's what I want, because I don't want a lawyer saying you've made it out. Yeah, that's another matter. Surely he would set up a methodology and let them get on with it. Why was he spending 15 years? Two questions occurred to me as one who has used a theodolite, never in anger. In my day, there was something called the Bowditch correction, and I think that was an instrumental thing because nowadays you have laser things, and this is a fundamental measurement question. Two things. You'd be very lucky to get church steeples and hills exactly at the same level. So immediately you're measuring up and down as well. So you presumably triangulate that somehow. That could be an issue. You can allow for the inclination, how you measure that. So you can triangulate in the vertical plane. The other thing is, did Gauss take account, if the distances are fairly long, the curvature of the Earth, which is a major problem of showing a flat surface on a map.
Oh,
He would know about that.
He would know about that.
So he would be bringing that to the party. I think nowadays, and this is my fundamental question to you, is that you have lasers, not my old sighting someone, getting crosshairs. And the maths, it got just really tedious, the calculations, I seem to remember. Therefore, you'd have two methods. You'd have the angle between the points, but every measurement could be within the limitations of laser coming back from a mirror. So every part of a triangle could also be a baseline. How would your method of squares take, if you've got two ways of measuring, how could it combine the two things, and could it see an error? Could you combine two methodologies? I'm talking about angles and baselines. Would that come into your methodology?
Okay, I have not thought about this before, but I think I'm pretty sure the answer is yes. Right.
Is there you were showing equations.
Equations, you just get more you
Yeah.
have more equations, you have more constraints, but the merit of this method is that it will work.
But I'm combining two methodologies.
That would work.
That could work.
That
Good.
could work.
Yeah, thank you. Excellent.
Okay, in the middle with the white jacket, if you could just hand it back.
Thank you. That was a great talk. I won't talk about cartography, which is a subject of interest to me. You mentioned the Russian school and sort of dismissed them, or maybe that was rude.
No, I'm sorry.
But they have an.
Was that Poincaré did not realize, although Laplace did this great work, probability was never very ceased to be was not fashionable in France. In backward Britain, it was really not. Right? There was a feeling that there was no progress in probability. But the Russian school took up these ideas, and already by the time Poincaré was speaking, they had good proofs of, not the proofs that I know, but good proofs of the central limit theorem.
Mike Jewess, just down here.
You mentioned the curves being symmetrical.
Yes.
Of course, a lot of curves are not symmetrical.
Okay.
And the obvious ones are velocities of molecules in a gas, where ultimately they can go up to infinity, and also salaries.
Okay. Well, this is going to be quite a long answer, because there are actually 3 points involved. If one is talking about, if one looks at things only in one dimension, yeah, there are a lot of asymmetrical curves. But if you say, well, I'm really working in 3 dimensions, then you have to produce very good reasons why you don't have spherical symmetry, right? Can't say, The second thing is that no, there is no statement that the normal distribution conquers everything. We know well that 20% of the people have 80% of the salary, right? That 20% of the wars produce 80% of the casualties, right? We'd simply have to say these are not covered by the hypotheses that we have, right? Nor, if we think about it, would we expect them to be, right? These are human beings. Bloody hell, right? It's more interesting when from time to time there do appear to be normal distributions. And again, you don't expect them to be entirely okay, but Quetelet, height and so on, they are roughly normal. They are not normal far from the mean, right? But if you're working to within 2 sigma to within 2 variations. Pretty interestingly close to normal, though not exactly so. The thing about you can't have a person of 0 size, but of course you can't have a person who's 50 feet tall, because that, yeah, it is not. You can use the normal, even if you realize that far away things are going to be different, right? So the angles at a church steeple can only add up to 360, right? So if you get the angle between 2 things to be 380 degrees, then you're a pure mathematician, right? So least squares, in theory, should take account of that. But you don't expect the errors to be that large. It's pretty good. It's a very good approximation where you're interested.
Okay. I think we've got time for one more question. That's at the back.
Thank you. If I understand you right, you said that Gauss derived his squares method from looking at the data of a series. Did he derive his method by looking at the observational measurements, or did he have some underlying theory by which he derived his method?
Well, he has Newton's theory of gravitation, I mean, which by then was known to be essentially correct. So he knew things like that it had to be an ellipse, right? So yes, he was working within a very strong pre-existing theory, which was very strongly established, a very strong established theory. But by God, look at the mathematics you have to do to get an orbit from that information. I couldn't do it. And I mean, he was doing all these things and taking account of errors at the same time. So, but he didn't disbelieve the underlying physical theory, the underlying physics he could take as being exact.
But what I really mean is, did he, on that basis, did he derive it just by looking at the experimental data, or did he have some underlying theory about how the experimental data would be, how the errors would work?
Only that, well, he believed that taking least squares would be an effective method, right? As I say, over the years he produced justifications for that. He didn't stop and say, well, I found series, you've got to believe me. He looked into the underlying mathematics, and Laplace looked into the underlying mathematics. But it's I mean, even when he did it, it was a plausible way of doing things. And it was the only way that you could do it, right? There's no other method available except least squares.
Okay, thank you very much. So I think we'll bring it to a close there. Can we thank Professor Körner again?